All right, so I want to do a little bit of a review from last time and just continue on from last time. So remember, we said this V star or V asterisk, whatever, is just a set of all f, the set of all extended real valued functions on a measurable set E. As always, E, yes, measurable. Where f of x is finite for almost every x in E, meaning f of x is a real number for almost every x in E. Meaning that the set of all x in E where f of x is either plus infinity or minus infinity has measure 0. Except on a set of measure 0, f is real valued. And yeah, remember the point is, this takes care of, functions we want to deal with, like the example I used all the time, just, x and minus 1/2 on 0 to 1, which is not too much of an exotic function because the improper integral from 0 to 1 is just going to be 2. So yes, it blows up at 0, but still it's a very practical function to look at. Okay, and the point here is that we want to somehow turn this into a vector space. We want to just be able to freely add. Forgot to say. This is we're assuming f is measurable. Right. So yeah, I definitely want to assume f is measurable. Okay. So remember we said for f g in this set here, we define the equivalence relation in kind of the natural way. F is equivalent to g if, practically speaking, for our purposes, they're kind of the same function in the sense that they're equal almost everywhere. Meaning the set of x where f of x, set of x in E where f of x is not equal to g of x has measure 0. Okay, and then, we said if G is in V star, then this is just set of all F star, where F is equivalent to G, right? On E. But implicit in this definition is, E is fixed, some fixed measurable domain. All right, and so what did we do last time? We said V is just a collection of all classes. The idea being, in all mathematics, whenever you deal with an equivalence relation and you want to look at equivalence classes, you're saying, well, I don't really want to distinguish between two different equivalent elements. And that's the same thing here. We don't really care if two functions differ on a set of measure 0. And that'll be, if you go through the integration videos, it'll be abundantly clear why we just don't care. We don't want to distinguish between two functions that differ on a set of measure 0. Sometimes you do, but for our purposes, we don't. So this is just a set of all classes for F and V star. And so in this perspective, it actually kind of makes sense to speak of a measurable element in V. And why is that? Well, basically, well, we proved that if two functions equal each other almost everywhere, then one is measurable if and only if the other one is measurable. So it doesn't matter what representative of this class you pick. If that one is measurable, then every other function, g, that equals f almost everywhere, and hence is equivalent to f, is also going to be measurable. So if one of these, if one function in this class is measurable, then so is all the other ones. Okay. And I should mention, if this is a little funky, it's not a huge deal. It becomes more important when we, well, when if you go further and study what are called LP spaces, which are extremely useful, and usually are on the usual prelim. This time they won't. But for us right now, it's not super important if this is a little wishy-washy. Okay, right. So remember, also, what did we do last time? Well, if f and g are in B star, we said IF is just a set of all x and e where, well, f of x blows up. So it's either plus infinity or minus infinity. Maybe a little clearer is to write it like this. IG similar. Right. And so because f and g are in V star, by definition of V star, both of these have zero measure. Okay. And so, right. So I think I use outer measure. Both of these are actually measurable. So assuming f and g are measurable. So yeah, in this set here, we observed has measure 0. Okay, so we can kind of begin to, kind of create. We can begin to create we can create an addition on V in the following way. Yeah, so we noticed last time that we can take f plus g, and it makes perfect sense as long as we're taking away, well, any possibility of either f or g being plus or minus infinity. You can always add two real numbers up. And on E, take away this union, both f and g are real valued. Okay. So, yeah, the point here is that on this set here, f plus g is real valued. Okay. I mean, technically, you can say it does. Yeah, it spits out real numbers, and that's all this means here. Okay. Okay. Right. So one thing to notice is that, well, certainly E take away IF union IG is measurable. E is measurable. IF union IG is measure 0. It's measurable. I mean, it's also measurable just because it has measure 0. Yeah, so certainly, well, maybe I'll prove, let me prove in a moment that we have a measurable function. Actually, I'll leave that for homework. I'll leave that for homework, that this function that we get here is measurable. Right. Okay, so yeah, kind of finishing up from last time, what did we do? We basically said, let this here be any extension whatsoever. We don't care at all what it is. You could literally make it plus infinity on IF union IG identically. We absolutely don't care. Let's give this a name, star here, this function. And so what do I mean by that? If it's not clear, I mean that when I take psi and I restrict it to E take away I, F union I, G, I just get F plus G. Or maybe a little clearer, same thing, psi just equals f of x plus g of x for x and E take away IF union IG. So that's what I mean by it's an extension of this function here. When restricted to this set, they're the same. Okay, so yeah, homework is that, as I mentioned, particularly, well, basically homework is that this function here is measurable, and also that this actually is measurable. It's pretty obviously finite almost everywhere, because IF union IG has measure 0, but homework is that, in particular, this is measurable. And it's pretty straightforward, but it's not, I mean, I wouldn't say it's trivial by any means. Okay, right, and last but not least, we define for any two classes, F and G, in V, we define the addition of these two classes as just this class here. Okay. And because this is in V star, this is going to be in V. Okay, so just as a sanity check, whenever, if you've taken any algebra course beyond linear algebra, you should remember that whenever you have an operation on classes, you really need to check, particularly if this operation on classes involves specific representatives of your classes, you need to check that this is well defined, meaning that it's independent of the specific classes we're dealing with. And this is no different. How do I define this? Well, this psi here obviously it depends on F and G. That's how we constructed it. We took F plus G. So take these two the class generated by F, class generated by G. Okay. Well, we're taking these two functions F and G and forming this function here. So this depends on F and G, and unless this is independent of the representative chosen, this doesn't make sense. So we need to check that. So let's do that. And again, this is more abstract than what we've been doing in the past, so it's not the biggest deal if this is a little wishy-washy. Okay, so why is this well defined? Well, what do I mean, I explained what I meant by that. And there's also the question of if we pick a different extension. Remember I said this could be any extension of f plus g where it's certainly defined. What if we pick a different extension? Does that give me a different class? I mean, I guess technically it may very well. Let's show that it doesn't. Let's show that no matter what representative of these two classes I pick, I'm going to get the same answer. Okay, so what do we need to show? In particular, if, let's say, we have just something in V that's equivalent to F. Let's say we have something in V that's equivalent to maybe it's not clear. Everything here is in V. Yeah, let's say I have something in V equivalent to G. And let's say, yeah, so let's say that I have, I mean, technically this even could be F and this could be G. Let's say I have some extension of F tilde plus G tilde. Let's call it, I think this is psi. I don't know, doesn't matter. Let's just put a tilde here. So let's say this extends this here. Okay. So I claim that doesn't matter. If psi is formed from F and G, and psi tilde is formed from F tilde G tilde, we don't care what the extension of psi tilde is, nor do we care what the extension of psi is. As long as it extends, then we're okay. Then we have the same class, and so everything is well defined. This is not a factorial. Well, I guess we should never use exclamation marks. Anyway. Okay, and this is really, it's not hard. It's just a bit of a pain. Well, no, it's not too bad. All right, so let's say A, lack of anything better to call it, set of all X and E, where f of x equals f tilde of x. B is a set of all x and E, where g of x is g tilde of x. Okay. Yeah, so what do we need to do? We need to show that these two we need to show that this is true. except on possibly a set of measures 0, these two are equal, or the set of all x where this is not true has measure 0. That's what we need to prove. Okay. So on E, take away this set. It's the union of 4 sets of measure 0, and hence has measure 0. Okay, so on this set here, what do we have? Well, we have psi tilde of x. So we're on a small, we're taking away possibly more than just if tilde. So we're certainly in the realm of, psi tilde is an extension of f tilde plus g tilde on E take away if union if tilde union ig tilde. So this here is certainly going to be, this is going to be f tilde of x plus g tilde of x. Because again, we're possibly taking away more than just if tilde union ig tilde. We're possibly taking away this chunk here, which maybe includes stuff not here. Okay, but right, f equals f tilde, g equals g tilde, certainly on this set here, because we're taking away all x where that's not true. So this is going to be f of x plus g of x. Well, again, right, so actually I need to union even more. I need the union of 6 sets, sorry about that. Let's also take away all x where f or g are plus or minus infinity. So now we have, because we're doing that, psi coincides with f plus g, as long as we're taking away if union ig. Okay. And by, so I don't want to write this whole thing, let's just call it, let's call this union of 6 sets C. It's just going to be 0 because all of these have measure 0. Okay. Each one of these 6 sets has measure 0, and we know, well, the countable union of sets of measure 0 is measure 0. So, okay, right. So, so what does this tell me? This set here that this set here is going to be in C. Okay. And the easiest way to see that is just take complements. This is equivalent to C complement is a subset of this complement on the left. And C complement is exactly this here. And on C complement, well, these two are equal. Okay. So the measure where these two functions are different is 0. Okay. Okay, so yeah, that takes care of the proof that this is well defined. Just some annoying technicality that we really just, in theory, have to deal with. In practice, well, yeah. So let me just talk about in practice, what you really do. So in particular, writing F class plus G class, well, it's really awkward, right? It's just incredibly awkward. So we don't do it. Yeah, so for two elements in V, writing, the addition of these two classes up with the brackets is awkward. Implicitly, what we do is we just say F plus G means this class here for any extension as we discussed earlier. Okay. So even though technically you can't add these two functions up pointwise when one is plus infinity or the other one is minus infinity, implicitly, because F and G are real valued almost everywhere, this addition has meaning, and it means this here. It means it's any extension whatsoever of F plus G where both are real valued. Okay. Right. And again, we don't care what the extension is. And the reason is, sound like a broken record, but I want to make sure that this really is clear. Yeah, any other extension size satisfies psi tilde rather. Yeah, being redundant, but just want to make sure that this is absolutely clear. Any other one satisfies, well, they're equal almost everywhere. And for our purposes, that means they're the same function. Okay. Yeah, I mean, I have to admit, I thought about, times when we really do want to distinguish between two functions that might equal each other almost everywhere, but at certain points are different. And I really don't know where you would really care all that much about yeah, I mean, there's probably certain applied math contexts where, you want to distinguish between functions that differ at all, but yeah. So it's tough to think of, where we care about differing on sets of measure zero. I can't really think of any. So anyway, all right. So another kind of note. So unless we're adding and subtracting functions, we are still okay with extended real valued functions that might be plus or minus infinity on sets of positive measure. So to make that clear, we're not adding and subtracting functions. So in general, we're just going to assume that we're dealing with a measurable unless otherwise stated. We're basically going to assume that we just have an extended real valued measurable function, and there's no assumption on the measure where f is plus or minus infinity. So to clarify that, the measure of all x and e, and this is measurable, so this set I'm writing is a measurable set. This is allowed. Right. That's the point. Unless we're adding and subtracting functions, we're okay with this f of x being plus or minus infinity on a really big set. I mean, you could even say f of x equals infinity everywhere. And I know particularly in physics, one example where you say, I think f of x is a constant on a finite interval, and infinity everywhere else is in the, if I remember correctly, the time-independent Schrodinger equation for the infinite square well. You have a potential that's just exactly what I described, something like that. So yeah, so in applied math, physics, you could definitely, you might want f of x to be plus or minus infinity on a big set. All right, so yeah, maybe I'll do an example here as a sanity check, kind of maybe get ourselves used to sets of measure zero and equivalent functions. So not the most general of examples related, you can do other examples kind of related to this, but so let's say I have two functions f and g. I guess I could have made this for homework, but let's say they are continuous. Then certainly both of these are in V. They're both real valued everywhere. And they're both measurable. Continuous functions are measurable. R is measurable. So in this case, these two classes are equal. F and G are equal to each other for almost every x and r, if and only if actually they're just identically the same function. And if you understand this concept, this proof should be pretty easy for you to do. I assigned it for homework. It should have been an easy homework. Yeah, so let's, easiest thing to do is to prove the contrapositive. So we're going to prove that that the converse of this, there exists x0 where f of x 0 is not equal to g of x0 is equivalent to yeah, this is equivalent to these two classes not being the same. Okay. Okay, so the proof of this, well, one direction is pretty trivial. So if these two classes are not the same, then the set of all, the measure of the set here is positive. These two classes being the same, so maybe these two are not equivalent, which is the same thing as saying, well, this has positive measure. Equivalency, by definition, is that this set has measure 0. So obviously, there exists uncountably many x where f of x is not equal to g of x. So in particular, well, obviously, if there's uncountably many, then there's one of them. So there certainly exists x0 where the two are not the same. And the other direction is not much harder. No, I mean, it's not that important, but just to clarify, you know, this is, yeah, there's, it's certainly uncountably many, in fact. All right, so, yeah, let's do the converse. So conversely, assume that, well, f of x0 for some x0, that f of x0 minus g of x0 is not equal to 0. Okay. So it's either positive or it's either negative. Okay. So this is a continuous function. By continuity, if f minus g at x0 is not equal to 0, you can find a little neighborhood where on the neighborhood it's not 0. Right, just basic analysis. For x and yeah, x0 minus delta, x0 plus delta. So that implies that the measure of the set here again, we're dealing with a measurable function because it's continuous, so right. So there's no issue. We're dealing with, yeah, we're, you know, f minus g is measurable. So set of all, yeah, I mean, yeah, if there's any doubts, just check that this is measurable, the set here, if you have any doubts. Just the measurability of f minus g, basically. So this, well, is certainly bigger or equal to, well, the measure of this interval, which is just 2 delta. Right. So that means these two classes are not the same. The set of all x in E, where f of x is not equal to g of x, does not have measure 0. All right, so let's move on. And I want to talk very briefly about a very important type of function that in some sense is, as we'll see in the next video, is kind of the building block of all measurable functions. And those functions are the characteristic functions. So let's say we have a subset of the real line. So for any x in the real line, so this is a function defined on the real line. Sometimes this is, well, let me just write the definition. So it's 1 if x is an A, 0 otherwise. Okay, so often this is written as 1A. It's sometimes called the indicator function. I'll stick with this notation. I think this is chi, but kind of almost looks like a hammer and sickle type thing, but it's not. It's chi, I think. I think that's the Greek letter. But anyway, so yeah, we have the following proposition. Very basic, but very important. That A is measurable if and only if this characteristic function here well, technically it's just an extended real valued function. But really, it's real valued, so I'm just going to get rid of this. Yeah, so A is measurable if and only if this function is measurable. And obviously, R is measurable. So, okay, and let's see how to prove this. It's fairly straightforward. So, let's first assume A is measurable. And let's say C is a real number. Okay, so you can really look at any of the 4 conditions that are equivalent to measurability. They're probably all equally easy. But let's just look at this interval here. Okay, so remember what the inverse image is. It's just a set of all x and r where, well, this just means that this characteristic function is less than or equal to C. So we need a bunch of cases. Remember, what is this going to be equal to? Just kind of remind you. Move this up a bit. Well, it's 1 if x is an A, 0 if x is not an A. So certainly this is empty if C is less than 0. This is never negative. So it's never going to be less than or equal to a negative number. It's the whole real line if C is bigger or equal to 1. It's always less than or equal to something bigger or equal to 1, because it's always either 0 or it's 1. And 0 and 1 are always, 0 and 1 is less than or equal to something bigger or equal to 1. Really not much to say otherwise. And last but not least, if the only other case is that C is between 0 and strictly less than 1, well, if X is an A, then this is 1, and 1 is not less than or equal to C if C is less than 1. Okay. But, yeah, obviously I can rewrite this as X is in the complement of A. Not that it matters much, but yeah, if X is in the complement of A, then this is 0. And certainly 0 is less than or equal to C if C is between 0 and 1, strictly excluding 1, including 0. So this is, this is basically the 3 possible cases. Okay. So what does this mean? This means that no matter what, this is a measurable set. Assuming A is measurable, because then the complement of A is measurable. Regardless of what C is, this is measurable. And there's really no need to, stray away from this kind of interval. So if this is measurable, then the inverse image, in particular, well, it's not very subtle what we want to plug in. This certainly works. This is, again, just write down the definition. Sorry, just having a little trouble with my pen here. Set all X and R where characteristic function of X is less than or equal to 0. Well, that's going to be a complement. So by assumption, this function here, because it's a measurable function, for any C, in particular C equals 0, this is a measurable. This is a measurable, a big measurable set. So a complement is measurable. That implies A is measurable. Okay. Obviously, if X is an A, then this is 1. 1 is not less than or equal to 0. If X is an A complement, then this is 0, and 0 is less than or equal to 0. Okay. Yeah, so not a whole hell of a lot involved there. All right, so I want to talk about compositions of measurable functions, and it's just a fact of mathematical life that compositions, unfortunately, do not behave all too well. Okay, so I claim. One second. That. Okay, so I'm going to make the following claim. There exists a measurable f that spits out stuff between 0 and 1. And there exists a measurable g that spits out stuff in 0 to 1. Where the composition G composed with F takes 0 to 1 spits out stuff in 0 to 2, is not measurable. Okay, and I'm largely just going to outline this. Okay, so by proposition 21 in the book, there exists a function from 0 to 1 that's continuous increasing strictly and onto, and thus it's bijection. Strictly increasing means it's one to one. And a subset S of the Cantor set and remember the Cantor set has measure 0, so S has measure 0, and so S is measurable. Remember the Cantor set is a subset of 0 to 1, where this is not measurable. Okay. So this function here, as nice as it is, it cannot be Lipschitz continuous. Remember that the homework that I assigned is that Lipschitz continuous functions map sets of measure 0. It maps measurable sets to measurable sets. In particular, it maps sets of measure 0 to sets of measure 0. So this here, is not measurable. So this can't be Lipschitz continuous. And yeah, so I'm not going to really go over the details of this. You can just go to page 52, and basically this, you can just go through the details here. The details are built upon the construction of the Cantor set, a little more technical than the Cantor set, I think. But it's built upon the construction of the Cantor set. And this is the part that we're really interested in, this part 2 here. Right. That this function here, strictly increasing, continuous, maps 0, 1 onto 0 to 2, hence its bijection. And it maps a measurable set that I called S, which is a subset of Cantor set, onto a non-measurable set. Okay. All right, so, right, how does this help me? Well, right, so let's say G is just, let's say F is the inverse function which goes from 0 to 2 to 0 to 1. And just by basic analysis, this is continuous, so it's certainly measurable. Okay, and let's say G be the characteristic function from 0 to 1, the characteristic function of S. And we're thinking of this as a function that's restricted to 0 to 1. Okay. So this function takes 0 to 1. Well, it spits out either 0 or 1, so certainly it takes 0 to 1 to 0 to 1. Okay, so I claim that big F is G composed with F. I'm not going to write the restricted because that's just silly. So this is not measurable. Okay, why? Right, well, let's just take the inverse image of 0 to 2. Right. Right. So if this was a measurable function, then we know that the inverse image of any relatively open set in 0 to 2 would be measurable. And we're going to show that this is not the case. Okay. Right. Second. Right. Okay. So this is going to be, just write down definition. This is a set of all x in 0 to 2, my domain function right here, 0 to 2. Yeah, just making sure. Oops. About that, this should be 0 to 1, 0 to 2 to 0 to 1. Sorry about that. Double check, this is fine. Yeah. Okay, so this is going to be, right, set of all x in 0 to 2, where characteristic function of psi inverse x is in 0 to 2. Obviously, if it's strictly between 0 and 2, then it has to be 1. Otherwise, it's 0. Right. So, right, this is a set of all x between 0 and 2, where, well, so when is this? Yeah, so this is going to be well, if and only if, yeah, as I said, obviously this characteristic function, plug this in as 1, which is true if and only if this is in S. Okay, this is equal to 1, this whole thing, if and only if psi inverse of x is in S. Okay. Well, yeah, this obviously equals set of all, because psi is a bijection. Well, this is just equal to psi of S, and this is not measurable. Again, here I'm using the fact that this is a bijection. So this is just all x in the image of psi. The inverse is an S if and only if x is in the image. Okay, so Right, so it's, yeah, an unfortunate fact. You can't compose two measurable functions to get a measurable function. The situation is not really dire. In practice, all you care about is really composing continuous functions with measurable functions. So yeah, we have the following. So let's say f, and I should just mention, yeah, technically I could have just said, well, this is the real line, this is the real line. I just want to emphasize that these functions here, you know, it's not even, you know, you can, you know, f here is even bounded. It's, you know, these functions spit out really innocent numbers. It's their, you know, f and g. You know, f is, yeah, f is a bounded function. So that's all I want to emphasize. Okay, so we have the following proposition. Let's say we have a continuous function f. And let's say we have a g. That's measurable. And let's say real valued. Okay, so the claim is that composition of f and g is measurable. There's not all that much involved in the proof. If theta is open, yeah, if we have any open subset of the real line, let's check that the inverse image of this function here is measurable. That's equivalent to this function being measurable. This is going to be G inverse image, F inverse image of theta. Well, this is measurable because, and this is the key here, this is open. Maybe I'll just circle it. By continuity, this is an open set. And we know the inverse image of an open set is open. Okay. So yeah, that takes care of the proof. All right, so yeah, we have an important consequence. Let's say we have a G, and this will be when we, you know, in future videos that look into integration, this is going to be extremely useful for particularly what are called LP spaces. Okay, so if we have a G, E is measurable. And this is measurable. Then the claim is that G to the P, here this is absolute value. Absolute value of G to the P is measurable if P is positive. And the proof is pretty straightforward. Give me 1 second. Check something quick. Okay, so right, so the proof of this is just simply just set f of x to be this concrete function, absolute value of x to the p. So g of x to the p is going to just equal f composed with g of x. And this is measurable because because f is certainly continuous on R as long as p, let's say as long as p, 1 second. Yeah, as long as p is positive. Okay, what I finally want to do is look at and prove that imps, soups, and pointwise almost everywhere limits of measurable functions is measurable. All right, so let's start off with proving that the maximum of a finite number of measurable functions is measurable. Okay, so let's say we have a sequence Fn of functions from E, just an extended valued function. Yeah, let's assume E is measurable. So for each natural number n, this is measurable. Yeah, I want to mention the previous proposition that we proved that if g is real valued measurable, then modulus g raised to the power p for positive p is positive. I'll leave it for homework for you to prove that this is also true if g is extended real valued, with the obvious meaning of, well, take absolute value plus or minus infinity. That's, you know, obviously has a meaning infinity, plus infinity. Raise it to a positive power. Obviously, this should be plus infinity. For some reason, the book does not, yeah, for some odd reason, the book does not give a proof for extended real valued functions, even though you really often do want to take the absolute value of an extended real valued function and raise it to the p. That's often extremely useful to do. But anyway, bit odd, but whatever. It's an easy proof, so that's why I'll give it as a homework. Okay, so yeah, let's prove the following. So if it's not clear, each one of these are measurable. Sorry, I didn't mean to do proof, I meant to write prop. So the following little proposition. So the maximum of each of these, I'll leave minimum for an easy homework. These are both measurable on E. Okay, so as I said, minimum is for homework. Let's do the maximum. So I claim that for any x in E, the maximum of all of these is bigger than C for some C positive. So let's just say C is something positive. Yeah, sorry, I meant to write this. I claim that this set here is going to be the union of these inverse images. The set of all x, well, it's just the union of these inverse images. Let's leave it at that. Okay, so why is this true? And, well, you just got to check it. It's really not too bad. So let's say the maximum occurs at some k0. And let's assume the maximum is bigger than C. Well, obviously this means fk 0 is bigger than C. So x is in the inverse image. Of C to infinity. Not a whole lot to that. It's bigger than C, so it's that. And obviously that's a subset of union. So this direction's pretty trivial. The other direction's not a whole hell of a lot harder. So conversely, if x is in, so let's say this is, I don't feel like writing this again. Let's call this blue star here, or blue asterisk, whatever. Well, yeah, it's basically almost, it's very similar. If x is in this union here, it's in one of these. So there exists k0. Maybe use a different integer or different integer between, whoops, sorry. Yeah, so a different integer between 1 and n. Where x is in this inverse image, which means that fk0 of x is bigger than C. Okay, what does this mean? Well, the max is the max. It's bigger or equal to any individual element here. I mean, it could very well be fm0 of x, we don't know, we don't really care. It's always bigger or equal to fk0 of x, which is bigger than c. Okay. So x is in the left-hand set, and that proves it. Okay. Right, and so yeah, that basically finishes up the proof because, well, I guess. So let me call, let's give this a name. Let's call this big, I'll use big F again. So what does this tell me? This tells me that the inverse image of C to infinity. So using other types of intervals to check measurability actually would be kind of tricky. So maybe this proof is not as trivial as I'm making it seem to be. The non-trivial part is picking the proper one of these four conditions that are equivalent to measurability that we start off with to work with. This is just the appropriate one. So this is measurable because, well, each one of these is measurable. We're assuming each f is measurable. And that's for any C and R. So big F, the maximum, is measurable. All right, and basically the same, very similar proof works for infs and infimums and supremums. So same assumption here. Each fn is measurable. Okay. So I claim. So yeah, I have the following proposition. The infimum, I'll write it like this. These functions here are both measurable. Okay, and like, oh, well, like before, yeah. I'll leave the inf for homework. So let's just do the soup. Okay. So I claim that, in fact, the supremum being positive so obviously, I don't think it should cause any confusion, but when I write soup k fk of x, I mean this here. So, yeah, so actually what I want to do is, like before, look at this set here. That, this, move this over a bit. Okay. And this function here, this is what I'm colloquially calling soup k fk of x. So I claim this is just the union of these sets here. And again, this is just a proper interval to look at. I should say for minimum, I mean, I'll give a hint for the homework when I assign it, but the minimum and the infimum, you're going to look at, I believe it's minus infinity to c. I forget exactly which, but it's going to be a more convenient interval than this. This is really what works for maxes and soups. Okay, right. And of course, I should say here, this is going to be this set here is the inverse image of this interval, c to infinity. That's exactly what this is. Set of all x where the sup is bigger than c. Okay. Now here is where we really want to allow our functions to be extended real valued. You could have a sequence of really nice real valued functions, and you just take the sup for a lot of x, that could be infinity. That's, you know, very practical. It's very not too funky. It just could be that. It could be for every single x, even though these functions are all nice and real valued. The sup for every x could be positive infinity. We want to allow that. Okay, so how do we prove this? Yeah, and I should say this supremum here, if this set here that I'm underlining is, I don't want to use blue. So we're going to say that the supremum is plus infinity if this set here in yellow is unbounded, not bounded above, rather. So if this set is not bounded above, then we say the supremum is infinite, which makes sense. I mean, kind of, yeah. Okay, so, right. So what's the proof here? So let's assume that the sup, and again, this just kind of goes back to my philosophy of you rarely, if ever, stray away from the definition of a sup. It's a supremum. It's the least upper bound. Okay. So if the supremum, yeah, if the supremum is bigger than c, then c is not an upper bound. For the set, I'm circling in yellow. Maybe I should put that in yellow. Why? Well, there's not a whole lot to that. Sup is the least upper bound. We have something smaller, so the sup can't be an upper bound. Sorry, the sup is the least upper bound. C is smaller, so C cannot be an upper bound for this set here. Okay. So what does that mean? That means there exists K0, that's a natural number, where fk0 of x is not less than or equal to c, it's bigger than c. So same kind of reasoning. X is in the inverse image of the set here. And that's a subset of, I'm not going to try and put it there. That's a subset of this union, obviously. Forget if I used N or K, it doesn't matter. Okay, so conversely, yeah, so if the soup is bigger, sorry, if X is in the left-hand side, so the soup is bigger than K, sorry, the soup is bigger than C, not K. The soup is bigger than C, then X is in this union. So conversely, let's say X is in the union. Okay, so if this is the case, then F is in the inverse image. Let's do the same thing. M0, I guess. For some M0 natural numbers. So what does that mean? Well, that means well, obviously the soup is it's an upper bound, so it's bigger or equal to fk0 of x. Well, fk0, m0. Well, f of m0 of x is bigger than c. So that implies that x is in the inverse image of the soup when you dump in c to infinity. The soup is bigger than c. Yeah, and that's really all there is to it. Right. I mean, that says that for any c whatsoever, the inverse image of the soup is measurable because we're assuming each one of these is measurable. Because each of the FKs is measurable. So one thing that I hope you're getting appreciation of is that you know, the sigma algebra rules of, you know, complements of stuff in a sigma algebra is in it. Countable unions is, and countable intersections is also in it. Particularly as it pertains to measurability, these rules are just so natural. You know, like we convert soups into countable unions just effortlessly. So it's, you know, the whole theory we just built is just going to work. It's just going to be, it's almost as if it's like tailor-made to do exactly what we need to do. You know, look at you know, the supremum or the infimum of functions. Looking at pointwise limits of functions, et cetera, as we'll do next.